Earth is not a perfect sphere. As Earth spins, gravity points toward the center of our planet, assuming for explanation's sake that Earth is a perfect sphere, and a centrifugal force pushes outward. But since this gravity-opposing force acts perpendicular to the axis of Earth, and Earth's axis is tilted, centrifugal force at the equator is not exactly opposed to gravity. This imbalance adds up at the equator, where gravity pushes extra masses of water and Earth into a bulge, or spare tire around our planet. Mother Earth has a generous waistline. At the equator, the circumference of the globe is 24,901 miles, 40,075 kilometers. Bonus fact, at the equator, you would weigh less than if standing at one of the poles. You may feel like you are standing still, but you're actually moving fast. Depending on where you are on the globe, you could be spinning through space at just over 1,000 miles per hour. People on the equator move the fastest, while someone standing on the North or South Pole would be perfectly still. Imagine a basketball spinning on your finger. A random point on the ball's equator has farther to go in a single spin as a point near your finger. Thus, the point on the equator is moving faster. The ground you're walking on is recycled. Earth's rock cycle transforms igneous rocks to sedimentary rocks to metamorphic rocks and back again. The cycle isn't a perfect circle, but the basics work like this. Magma from deep in the earth emerges and hardens into rock. That's the igneous part. Tectonic processes uplift that rock to the surface, where erosion shaves bits off. These tiny fragments get deposited and buried, and the pressure from above compacts them into sedimentary rocks such as sandstone. If sedimentary rocks get buried even deeper, they cook into metamorphic rocks under lots of pressure and heat. Along the way, of course, sedimentary rocks can be re-eroded or metamorphic rocks re-uplifted. But if metamorphic rocks get caught in a subduction zone where one piece of crust is pushing under another, they may find themselves transformed back into magma. Because our globe isn't a perfect sphere, its mass is distributed unevenly. And uneven mass means slightly uneven gravity. One mysterious gravitational anomaly is in the Hudson Bay of Canada. This area has lower gravity than other regions, and a 2007 study finds that now melted glaciers are to blame. The ice that once cloaked the area during the last ice age has long since melted, but the Earth hasn't entirely snapped back from the burden. Since gravity over an area is proportional to the mass atop that region, and the glacier's imprint pushed aside some of the Earth's mass, gravity is a bit less strong in the ice sheet's imprint. The slight deformation of the crust explains 25% to 45% of the unusually low gravity. The rest may be explained by a downward drag caused the motion of magma in Earth's mantle, the layer just beneath the crust, researchers reported in the journal Science. Earth has a magnetic field because of the ocean of hot, liquid metal that sloshes around its solid iron core, or that's what geophysicists are pretty certain is the cause. This flow of liquid creates electric currents, which, in turn, generate the magnetic field. Since the early 19th century, Earth's magnetic North Pole has been creeping northward by more than 600 miles, 1,100 kilometers, according to NASA scientists. The rate of movement has increased, with the pole migrating northward at about 40 miles, 64 kilometers, per year currently, compared with the 10 miles, 16 kilometers, per year estimated in the 20th century. Over the past 20 million years, our planet has settled into a pattern of a polar reversal about every 200,000 to 300,000 years. As of 2012, however, it has been more than twice that long since the last reversal. These reversals aren't split-second flips and instead occur over hundreds or thousands of years. During this lengthy stint, the magnetic poles start to wander away from the region around the spin poles, the axis around which our planet spins, and eventually end up switched around, according to Cornell University astronomers. Earth may once have had two moons. A teensy second moon, spanning about 750 miles, 1,200 kilometers, wide, may have orbited Earth before it catastrophically slammed into the other one. This titanic clash may explain why the two sides of the surviving lunar satellite are so different from each other. Some scientists claim Earth has two moons currently. According to researchers reporting in the December 20, 2011, issue of the planetary science journal Icarus, a space rock at least 3.3 meter, 1 meter, wide orbits Earth at any given time. They're not always the same rock, but rather an ever-changing cast of temporary moons, say the scientists. Their theoretical model posits that our planet's gravity captures asteroids as they pass near us on their way around the Sun. When one of these space rocks gets drawn in, it typically makes 3 irregularly shaped swings around Earth, staying with us for about 9 months before hurtling on its way. Earth used to be purple. Well, life on early Earth may have been just as purple as it is green today, suspects Shildas Sarma, a microbial geneticist at the University of Maryland. Ancient microbes, he said, might have used a molecule other than chlorophyll to harness the sun's rays, one that gave the organisms a violet hue, he suggests. Das Sarma thinks chlorophyll appeared after another light-sensitive molecule called retinol was already present on early Earth. Retinol, today found in the plum-colored membrane of a photosynthetic microbe called halobacteria, absorbs green light and reflects back red and violet light, the combination of which appears purple. The idea may explain why even though the sun transmits most of its energy in the green part of the visible spectrum, chlorophyll absorbs mainly blue and red wavelengths.